Hey gang, all right, video number 3. So it's just design group and me then. Excellent, well done. PJ's still in the room. He's moved to the back of the room though. He's trying to avoid us. He can't handle the pressure of the science. So anyway, this is the third of the 3 videos. The last one, you're almost there. This video is going to deal with science instrumentation. The purpose of this video, basically, you've watched the first video that talked about the intro, the overview of Europa and Jupiter. Kind of gave you some ideas of stuff we know and don't know about Europa and Jupiter. Second video tried to put an exclamation point or a question mark after that, saying, okay, these are the things we know and don't know. These are the things that NASA's interested in. Here's some potential science objectives you could think about. This video, excuse me, the purpose is, okay, we want to, our team wants to discover if there's subsurface oceans, or our team wants to discover how thick the ice is. How do we do that? What do we measure? What are we actually going to do to measure that? That's what this video is to help you figure out how to actually measure, how to actually accomplish your science objective. That's what this is going to try to do. And this doesn't work for everything, so if this video doesn't end up helping you with your science objective, just let us know in class, and we'll kind of give you some feedback on that. So, science instrumentation. So outline, well crap. Basically, like I talked about in the previous video, there's atmospheric and surface measurements you can do. There's subsurface measurements on Europa you can do. There's plume measurements also. There's Jupiter measurements also. But I'm gonna skip those because those are kind of covered up here as far as how the measurements are accomplished, how those science objectives would be accomplished. And we're gonna jump to how temperature and heat flow work, and then we'll talk about the tables. So inside of these categories, I will talk to you about different ways to measure different science objectives. And hopefully your objective will be covered in one of these. If not, we'll talk about it later. And then at the very end, we're going to talk about the 3 tables that you have to complete. What's going to happen, you're watching this on a week we're not visiting you guys. Next week we're going to visit you guys, and you're going to give us the team progress report. And we expect to see these tables at the team progress report. They might not be complete, but we want to see at least what you've been working on so far. At your team, at your team progress report. So, all right, let's just get with this. Remember, there's 2 types of measurements. Basically, 2 types of measurements. There's properties and composition, and we're talking more about what properties and composition are right now. So, atmospheric and surface properties and composition. There's 2 basic properties and composition. Properties are the qualities of something, the qualities of whatever you're measuring. That's the properties. In this case, atmosphere or surface. Pressure, temperature, density, viscosity, charge, pH, wind speed, humidity, amount of lightning, precipitation, whatever. Those are properties. Composition is the constituents of the atmosphere or the surface, or the constituents of whatever you're measuring. That's composition of something. And composition are the elements, the compounds, the ions, salts, acids, bases, minerals, metals, biologicals. That's the composition of something. Properties are the qualities, composition are the constituents of it, okay? You can measure properties or composition, or you can measure both of them. Sometimes it's hard to measure both, but the both is what scientists really want, but that takes a lot of mass, and you guys only get 5 kilograms. So for the surface, soil mechanics, penetrability, hardness, that's also a property of the soil you can measure, or of the surface you can measure. So again, properties, here's a list of properties. Pressure is measured by, here's the list of the properties and how they're measured. So, and you can look at this better when you look at this. This is on the downloads page. All the presentations are on the downloads page. Go and grab this, because this will tell you, this is small font, and this will give you some information that you can't see on this video. Pressure is measured by a pressure probe or a pressure transducer. It's a touchy measurement. You actually have to touch, the pressure transducer actually has to feel and touch what the pressure that's being measured, okay? It's a touchy measurement. I'll explain more about that. Temperature is measured by a thermocouple. It's also a touchy measurement. I'll explain how thermocouples and pressure transducers work at the end. Density it's mass over volume. You guys know this, right? So it's two measurements, an indirect measurement to measure density. You have to measure mass and volume. It's difficult to do, actually. And indirect viscosity, there's viscometers, whatever, viscometers, and there's rheometers. Viscometers and rheometers. I can't speak. I did all these 3 presentations back to back. I can't speak. You can also measure how fast something falls through something. That's viscosity measurement, stuff like that. You guys are familiar with the word viscosity from like motor oil and stuff. Charge is electrometers or a galvanometer. It's a touchy measurement. Also, you actually have to touch the charge that you're measuring. Also, charge is something that's based on, charge is not something, just a number. Charge is based on a relationship. Usually it's to ground, okay? And so you can't just measure a charge by itself in the middle of nowhere because there's no reference point. Charge requires a reference point, basically. So if you want to measure charge of an atmosphere or something like that, you have to have a reference point that you're measuring it against. And if that's we can talk about this if this is what you want to do. pH, you guys know what pH is, right? If you've ever like looked at a pool or something, right? You ever done the chemicals for a pool? pH, you can use electrodes, pH meters, or indicators. Remember the litmus test? They'll do that in chemistry class, the paper that turns blue or red or something. It's a touchy one, it must touch. Wind speed, you can use an anemometer. Those are the cups that are on top of the car, you know, like the storm chaser vans, that's an anemometer. The cups that spin around, that's an anemometer. An accelerometer can also be used, or an IMU. Accelerometer or an IMU is an inertial measurement unit. We'll talk about both those in a minute. But those can be used to calculate wind speed indirectly. And an anemometer calculates it directly, but an anemometer requires something to be stationary. Either the wind to be stationary or the thing to be stationary, because it's a, it's a motion thing. It's a direct measurement. So humidity is a hygrometer. It typically requires temperature, pressure, and mass measurements also, because humidity is a complex. It's a complex thing to measure. And precipitation is a rain gauge. There's optical ways to measure rain, or there's other ways to measure rain too. Like a rain gauge, you go out, you look at it, right? You go, oh, about 2 inches. So how do you know that? Or there's, your gas tank in your car basically is a measurement of a fluid level without looking at it. So there's ways to do that, but there's not any rain on Jupiter on Jupiter or Europa. Yeah, let's call Jupiter and Europa's what is it there? Their Hollywood name would be Jupiter, right? Let's start calling it Jupiter. Like Benifer or somebody. What's another one? Like Brad and Jennifer was Benifer. I don't know. Anyway, so those were properties. Those are a bunch of different properties. There's more properties, but those were a smattering of properties. Composition. Composition is the elements and the minerals and the compounds that make up something, the constituents of something. And it's typically measured by a mass spectrometer. And a mass spectrometer, it's just what it sounds like. It requires a mass of something, and the mass could be a gas as well. Actually, there are only 2 kinds of mass spectrometers: solid mass spectrometers and gas mass spectrometers. There's no such thing as a liquid one. If you want to measure the properties of a liquid, you have to make it boil first and turn it into a gas. So, mass spec for short, it's an analytical technique. Essentially, it determines the masses of the particles that are inside the thing that you want to know the composition of. And from those masses, it can determine what it is. It works by ionizing chemical compounds. This is really complex, but I'll tell you how it actually physically works in a second. So basically what a mass spectrometer does is, and we have these on like all these Mars rovers and stuff that take all these selfie pictures, like, hey, I'm a Mars rover, and they take their selfie. They all have mass spectrometers all over them. And there's different kinds, and they work differently a little bit, but the basic principle behind a mass spec is, oh cool, I have a laser here. So there is a substance, there's a thing you want to know, okay, what is this made of? What is this made of? And here's your mass spec, and the mass spectrometer shoots a laser at the thing you want to know. It makes that noise. It goes, it shoots a laser at the thing you want to know the composition of. And what happens is, right next to the laser that shoots out, there's a camera, essentially. and the camera watches the laser as it shoots out. When the laser hits the thing, the unknown substance, it lights up. It gives off light. It fluoresces. Okay, and when it gives off light, it gives off a spectrum, mass spectrometer, mass. So there's a mass of something, and it gives off a spectrum, mass spectrometer. So this laser, you know, here's the mass spectrometer, right? Here's my mass spectrometer. It shoots out a laser at the unknown thing. It hits the unknown thing. The unknown thing lights up right next to the laser. There's a camera watching all this happen. You know, this camera's watching it, and the camera determines from the light that is emitted back at it. The camera determines what the laser hit. Okay. So we do this all the time with the Mars rovers. Okay. There's two basic functional types of mass spectrometers, and in the Matt Turner version of them, I call them internal and external. There are internal mass spectrometers where you take an unknown substance, like you scoop up some unknown dirt off of Mars, and then you stick it in your easy bake oven, and then inside the easy bake oven, the laser hits it, and then the little camera watches the laser hit it, and the laser hits the thing, and it fluoresces, and then the camera sees it and it goes, oh, okay, there's some sulfur in there, there's some carbon in there, and there's a Snickers bar in there, you know. So the the camera watches it inside this chamber, this box, inside of a box essentially. So, but you have to get the stuff inside of the box, right? How do you get the stuff inside the box? That's the hard part. That's why rovers always have arms and scoops and stuff. That's the internal mass spectrometer, okay? External mass spectrometer works the same way. Laser with a camera that watches the laser hit the unknown thing, but it does it outside. It does it in open space. So the Mars rovers, they've got these long arms. At the end of the long arm, they have what's called the RAT, the rock abrasion tool. And the rock abrasion tool, basically it's a little drill, and they go in and they drill a little hole in a rock, and then the drill backs up, and then it shoots a laser beam where it just drilled a little small hole, right? Because, huh?
How does it get?
And so the laser beam hits the little hole that was just drilled with the rock, because they want to know what does the rock look like inside. But this occurs outside. It's not in the easy bake oven because the rock is too big to pick up. And so so it shoots it, and the laser hits it, and then it fluoresces back, and then the same principle. It sees the spectrum, and from that spectrum it says, oh, there's carbons in there, there's nitrogens in there, there's xenon in there, okay? And boom, it works. Now, the internal ones are more accurate because you're inside of this closed container, there's no light around, they've sealed it off, they know what the conditions in this container are. It's a very accurate, precise measurement, more precise measurement. The outside one, the external one, you shoot in this laser, it's going through air, going through some sort of gas before it hits the unknown substance. So once it hits the unknown substance, it's already gone through this much or whatever, you know, this far of gas between the laser and the unknown substance. There's also light. There's ambient light around. There's the sun or whatever, or a flash or whatever from the if the rover has a light on it that it uses to look at, you know, where it's shooting and stuff. And so the external version of the mass spectrometer, typically they're lower mass, they're easier to use because you don't have to get the stuff inside the easy bake oven, but they're not as accurate because of the ambient light and because the laser is passing through a gas that it doesn't know what the gas it's passing through is, right? Typically they'll calibrate it, it'll take a step back and calibrate itself, you know, saying, oh, okay, the gas around here is, you know, oxygen and nitrogen. But it's less accurate than the easy bake oven technique. So those are the two types. So mass spec, laser beam hits something unknown. The something that's unknown fluoresces. It gives off light. It gives off a spectrum of light. There's a camera next to the laser. It goes, okay, I just saw that. Okay, there's carbons in there, nitrogen, oxygen, xenon, whatever. There's some. That's what's in. You know, that's what's in what I just saw. That's how it works. And there's internal and external. There's the easy bake oven, or there's the shooting the laser out through and hitting a rock. So that's the very, very nutshell version of mass spectrometers. So, and that's how you measure composition, by the way. That's all composition measurements are. Mass spectrometer is how you measure composition. Pretty much it, okay? So if you want to measure composition, you're going to use a mass spec, okay? Just FYI. So many measurements, there's issues with property and composition measurements, as I'm sure you've determined so far. Many property measurements are touchy. You have to touch what you're actually measuring. That might sound like a not so big deal, but it is a big deal when you're dealing with space, dealing with things that are extremely hot or lots of radiation. You want to keep your instruments protected, but you have to have something touch something else in order to take a measurement. It makes it more difficult. Some properties can be inferred, measured indirectly. Spectrometers are not robust. They're not known for being able to hit the ground and survive, because there's a laser involved. There's a laser that has to hit something, and then there's a camera that has to watch the entire thing happen. There's a lot of precise things that go on for the mass spec to work properly. So they're not really known for being robust or being able to put up a fight if they fall or hit the ground or something. Geologists carry these. There's some handheld ones. It looks kind of like a really big iPhone or something. It's almost like it's like a big handheld. They're called rock hounds that geologists carry. And geologists, when they go out in the field and stuff, they like jump over rocks and and mess around. And they can handle like a 6-foot fall to a rock, and they won't break. But above that, game over. So mass specs, not the most robust things. They can maybe tolerate 30 Gs. There's a trade. Internal spectrometers are more accurate, but external ones are easier to use and usually less massive, like I just said. So, properties and composition. That was properties and composition in a nutshell. All of your measurements are going to deal with properties and composition, unless you do internal structure is a little bit different. That's still, we'll talk about that in a minute. There's still some properties really, but 90%, 99% of the measurements you will take are properties or composition. So they will all relate back to those previous slides I just talked about. And if you're doing composition, you're going to have a mass spectrometer, okay? By the way, there's examples of all these instruments. If you're like, well, I don't know where to get the instruments from, there's examples in the notebook, in the engineering design notebook, okay? So use that, use this chapter, and use this presentation as well. It's on the downloads page. So internal structure. So how do we know? You guys have seen the drawings of Earth. Earth has a crust, right? It's so many feet thick or so many miles thick, and there's a mantle that's like this thick, right? And then there's the core, the molten core that spins around, There was the movie called The Core. That movie was so bad, it was actually good. It kind of went full circle, There's that one point in the movie where they where they deploy directional nuclear bombs to restart the core of the Earth. It's so awesomely bad. It's got the guy, DJ Qualls, a real skinny guy who was in Road Trip. He was in it. He's like the geek in it. And at one point he's like, I'm going to hack the internet. I'm like, oh my gosh, I'm embarrassed for this movie. But anyway, so The Core is a great movie if you want to learn about, internal structure. Anyway, so internal structure of a planet. How do we know what the Earth looks like inside? We've never been there. The deepest we've ever drilled into the core, into the surface of the Earth is not that far, maybe a few miles. We haven't even gotten to the mantle part of the Earth yet. We've never even come near the core, right? So how do we know what the Earth looks like? I'm about to tell you how. Okay, so internal structure of a planet can be, you can determine the internal structure of a planet without actually looking on the inside of the planet. What we do is we use vibrations. We use earthquakes, or if we're not on Earth, we use a quake on another planet, whatever, like it's on Venus, it's a Venus quake. We use the movement, the quakes in the planet itself to determine what the planet looks like on the inside. I'll tell you how to do it in a second, in a second. But when you're determining internal structure, you're not actually measuring internal structure. You're going to be measuring vibrations, okay? That's the difference. I want to make sure you guys get that. So when you're looking at internal structure measurements, you're not going to pull out your internal structometer and put it on the ground. There's no such thing. What you're going to be measuring is actual motion, vibrations. That's what you're measuring, okay? Now tectonics, you guys have heard of plate tectonics, right? It's the motion of plates. Earth's crust has plates that move around independently. They don't know about Europa. Europa's got this icy shell that's one big thing of ice that's getting squeezed. But below that, below the ocean, there is a rocky surface, they believe, right? Does it have plates? Do these plates shift around? Is it seismically active down below? They have no clue, okay? So some planets don't have plates. Venus doesn't have plates, for example. However, there is activity inside Venus that also creates vibrations and motion. Earth's vibrations and motion are created by movement of plates. So that's how Earth creates its earthquakes and vibrations, just these plates shifting around. Other planets do it differently. But basically all you need are these vibrations, this motion, this large-scale planetary type vibrations and motions in order to use this technique. So, and fortunately Europa has that, because it's got this tidal flexing that is constantly being squeezed and pulled by Jupiter and the other planets and the other moons around it. So it may or may not have plate tectonics, we don't know. But it does have enough movement and vibrations and motion in order for us to use the same technique at Europa to determine the internal structure. Capiche? Everybody follow so far? So how does this work? Has anyone ever had a CAT scan? With a CAT scan, what they do with a CAT scan is you stay completely still, and there's one collector, right? But with a CAT scan, what they do is they move this energy source, this scanning machine all around you, and they take different planes, different scans, and then they go and they put all the scans together and make your head or something, right? That's how a CAT scan works. It's got the energy source moves around and sends different scans, and there's one detector at the back that, that detects everything. That's how CAT scans work. Internal structure of a planet is just the opposite of that. There's one energy source, one quake, one vibration that is felt, but there's multiple detectors all around, okay? So what happens, let's shift to this slide. On Earth is you'll have an earthquake, something, let's call the earthquake, is that whatever this spot is right here. There's an earthquake and it shakes. All over Earth, we've got seismometers set up all over our planet. There's actually one near my house. It's kind of cool. Excuse me. We got seismometers set up everywhere, on the land, in the ocean, at the bottom of the ocean, everywhere, okay? And so when there's a quake that's felt, it's felt it's felt here first, right? Time-wise, it's felt right here first. So the sensors that are near the quake feel the quake first, and feel the quake the strongest, right? They feel the strongest. However, the vibrations are sent all throughout the planet, They get to these different points at different points in time, right? And so the different sensors sense them at different points in time, and they sense the waves, the vibrations that are sent through the Earth change by the time they get to the different sensors, okay? Because they've gone through different material. They've gone through either just the crust by itself, they've gone through the crust in the mantle, or they've gone through the crust and maybe the core, So the waves have gone through different material, and as the waves go through different material, they change. The waves change. So if you get enough sensors set up, and if you have enough of these quakes, enough of these energy disturbances, enough of these vibrations to go through that you can take different measurements, you can start to make a picture of the inside of a planet based on that. Does that make sense? Because there's different types of waves. There's P waves and S waves. S is shear waves, P waves are compressional waves. There's also surface waves that don't really have a name because S is already taken. Anyway, so what are you going to do? So certain waves, like S waves can't travel through liquid because it's a shear wave, and you can't send a shear through a liquid. And so that's how we know that there's a core, a molten core on the inside, because when there's a quake here, the other side here, all we get are P waves. There's no S waves. So they know that the S waves stopped somewhere in there, and we have enough measurements that we can determine how big the core is, stuff like that. So that's how this works. That's how internal structure of a planet works. Basically, you use the vibrations that the planet creates on its own, earthquakes or through tidal flexing or whatever activity is going on the planet. There's usually some sort of activity going on inside of a planet. You use those vibrations, those waves that go through the planet, and you just detect those waves at locations all around the planet, and you put them together and make a 3D image, essentially. And those waves give you the picture. Does that make sense? Cool, good. So here's another graphic of it, the same thing, earthquake, and the waves go through, and S waves can't go through the core, so they stop. P waves only go through. There's shadow zones. The waves are also deflected as they go through different things. They're either, waves could be amplified or subdued, or waves could go off at a different angle, those types of things. And that's how scientists who are much smarter than me have put all this together for Earth. And they want to do this for every planet in the solar system. On our moon, we've sent, how many astronauts have been to our moon, PJ? Like a dozen? Sure. Yeah, about a dozen, maybe 14 astronauts have been to our moon. We've put seismometers as many places as we can over our moon because we want to know the internal structure of our moon. You counting them? Use Wikipedia. You got a computer. 12. 12? Okay, a dozen. I was right.
14, but...
That's right. Yeah, Jim Lovell. Sorry. So that's how we get pictures of the internal structures of planets. Now, scientists want to know this about Europa. They want to know, they're desperate to know this about Europa because there's the whole thick versus thin ice debate. And I know you guys, I know there's probably in your room probably already the fights broken out about thick versus thin ice. I'm sorry. Please, let's keep this professional. But they want to know if there's a subsurface ocean. They want to know how thick the rocky area is. Is there a metallic core? They want to know all these things. All these are internal structure questions, and we're not going to be able to dig down in there. We can't do that. It's impossible. But we can use internal structure type measurements, seismic measurements, in order to determine what the planet looks like on the inside. Because we don't know if there's quakes on Europa, but we do know that Europa is getting squeezed and pulled and squeezed and pulled. So those vibrations will be felt throughout the entire planet, okay? And so we can use those vibrations to develop a picture of the planet if we want to. So how does a seismometer work? You guys have seen like old school seismometers, right? Like on Scooby-Doo and stuff. A big roll of paper, and there's a mass and a spring and a pencil, essentially, right? And basically, as the ground moves, the seismometer stays stationary, and it creates the big, that's where it draws things, right? You guys have seen those before, right? Well, these still might exist somewhere in a big room somewhere, but most seismometers, most things that we use to detect quakes now are all digital or electronic, and they're more accurate, and they're much smaller. They don't need a big roll of paper anymore. So basically, the wave moves this thing, and this thing stays. That's how they work. One thing has to move, and one thing moves slower or stays independent of the motion. That's how they work. We can do this electronically. It's very easy to do. So seismometers are the more advanced way to do it. They're very accurate, advanced way to do it. However, recently we've come up with small digital devices called accelerometers. Accelerometers, you guys might not know this, but there's accelerometers. You're very familiar with accelerometers because there's accelerometers on every single smartphone. How does your phone know when it's this way versus this way? Or how when you're playing Cube Runner, how does your phone know if you're twisting it? How does it know? Well, it basically knows from accelerometers. Actually what it has on the inside is an IMU. I'll explain the difference in a minute, but basically an IMU is a fancy accelerometer. And what's really cool is that accelerometers behave a lot like seismometers, okay? They might not be as accurate in some respects as seismometer, but they behave very similarly to seismometers. Furthermore, they are more robust than seismometers, and they're cheaper and smaller than seismometers. And the really cool part about it for you is that if you wanted to measure wind speed, if you wanted to measure wind speed of the winds on Jupiter, how do you do that? Because an anemometer, the cups that spin, like you see the storm chaser vans, right? They park, and the cups that spin around, they move real fast. That's how they measure wind speed, right? That's because the van's not moving. If you send a probe into Jupiter, your probe is moving, right? So how are you going to determine what motion is from the probe moving and what motion is from wind speed? Okay? What you can do is you can measure accelerations, because there's a relationship between acceleration, velocity, and position. It's calculus. I don't want to scare anybody, and so by saying the word calculus, you don't have to know how to calculate the relationship, but just know there is a relationship between acceleration, velocity, and position. Basically, position is distance as well. So the first derivative with respect to time of position is velocity, and the first derivative with respect to velocity, the first derivative of velocity with respect to time is acceleration. And you can integrate in order to go from acceleration to position. So there's a relationship there that we can exploit to measure, because an accelerometer, it measures accelerations, but from that you can determine how far something moved, how much it moved. And that's vibration. That's a vibration measurement, right? That's what you want to measure for internal structure, right? That's also what you want to measure for wind speed, is how much something moved. So the positional measurements are what you're looking for. We just use accelerometers to take positional measurements. Does that make sense? Okay, now this is new for Inspires because we've had to get fancier with Inspires because the students are getting smarter and the judges are getting smarter too. There's something called an inertial measurement unit, an IMU. Spacecraft have IMUs on board. Actually, that's what really exists inside your phone is an IMU. An IMU is essentially a 3D accelerometer. Now accelerometers, I didn't mention that before, but accelerometers can work in one dimension, like up, down. You know, they can work in one dimension, or they can work in all 3 dimensions. You know, up, down, this way, or this way. 3-dimensional accelerometer, okay? Now, an IMU, inertial measurement unit, basically it measures, for spacecraft or for planes and stuff, it measures the craft's velocity, orientation, the gravitational forces that are on the craft at that point in time. They're very important for spacecraft. That's how a spacecraft knows where it is in space and knows which way it's facing, is its IMU. That's how it always knows which way is up, because when you're in space, which way is up, right? But the spacecraft knows which way to turn, which way it's facing, okay? Because of the IMU. So an IMU is essentially a 3D accelerometer and a 3D gyroscope. You guys know what gyroscopes are? Gyroscopes, basically it's a thing that spins around and it knows if it's being twisted or moved. You guys have seen them before. You probably did a lab on it in a class or something. But it's something that spins, it's a spinning thing, and then if it moves it off axis, it feels that force and it can measure how far it's moved. So it knows its orientation in space without having any other information, just because it knows where it started and it knows where it ended. That's what a gyroscope is. An accelerometer measures acceleration. So if you have both of those, if you have accelerations and orientation measurements, you can determine where you are in 3-dimensional space and which direction you're facing in 3-dimensional space. That's an IMU, inertial measurement unit. Some IMUs are more advanced than that. The ones that are meant for Earth especially, they have magnetometers on board because Earth has a magnetic field that they use. We can use Earth's magnetic field to measure orientation. And some even measure pressure so that it can tell where it is in altitude-wise if it's in the Earth's atmosphere. This might come in handy if you're on Jupiter to measure pressure measurements, or on Europa if you're measuring the thin atmosphere as well. Now, magnetometer-wise, the ones that are for Earth are calibrated for Earth. The IMUs are calibrated for Earth to tell you they use magnetic field measurements to know its orientation in space. The magnetometer wouldn't work in that same way on Jupiter, but it would still measure magnetic fields on Jupiter or on Europa. Does that make sense? So, but an IMU is basically an accelerometer plus a gyroscope, and this is how we take an accelerometer is what you're going to use to measure position, because every single payload, everybody that can hear me right now, and even those who can't, even those who've fallen asleep already, you're going to have an IMU on board, okay? You're going to have something that measures your position and your orientation. You have to, because every one of you has to deploy. You have to be autonomous. That's one of your requirements, is to be autonomous. And there's no GPS on Jupiter. There's no GPS on Europa. GPS is a satellite system that we have on Earth. That's how GPS, that's how your GPS in your phone works. That's how GPS, in your car works. You can't do that on Jupiter or Europa. But what you can do is, if you start from a fixed location, from a known location, and then you're deployed, you can take measurements, you can take acceleration measurements and get position from that, and then you can take orientation measurements and know which way you're facing from that. Does that make sense? So if you're right on the you're like this is a spacecraft and my phone is your payload, and the spacecraft knows where it is in 3-dimensional space and in space, because spacecraft has star trackers that look at stars and they know where they are. It also has some really advanced IMUs. And so your payload is deployed, right? And then when it's deployed, it's no longer with the spacecraft. And so the spacecraft can no longer tell this where it is. But what your payload can do, start measuring with the IMU and the IMU can tell it, okay, you've traveled, you've felt these accelerations, so it knows the accelerations you're feeling and how long you felt the accelerations. It knows if you're spinning because it knows its orientation. So the IMU can tell you how far, based on this relationship here, based on the acceleration, velocity, and position relationship, the IMU can tell you your position from a start point. From a known start point, the IMU can tell you where you ended up. Like if I were to take my phone and turn on my IMU and then I'd toss it to PJ, I'd turn off the GPS because the phone wouldn't know that it's in Huntsville, Alabama, but the phone would know, hey, I just traveled 5 meters in that direction, and I flipped over one time while I was traveling in that direction. That's how an IMU works. An IMU can't tell you I am in Huntsville, Alabama, or I can't even tell you that it's on Earth, really, but what it can tell you is that it's traveled 10 meters, in this direction, and it's felt these accelerations, and it's flipped over 6 times while it's traveled. It can tell you that. So if it knows where it starts from, you can determine where it ended up based on, you can back calculate where it ended up based on the measurements the IMU took. Does this make sense? I hope this makes sense. Is this making sense to you, PJ?
Sure.
Okay. So you guys have got it. We'll talk about this more. It's a little confusing, but you can use the IMU because the relationship between velocity, between acceleration, velocity, and position, you can use the IMU to determine where you end up, essentially. So, also you'll use an IMU and an accelerometer to determine internal structure. So the issues with internal structure is you have to have a network. I told you that on Earth we've got what? You have to have a network. He's making fun of me in the back of the room. It's not helping me. You have to have a network of sensors. Now what is a network? That means at least 3. You have to have at least 3 sensors to determine internal structure. The more sensors the better, obviously. And the further apart they are, the better. The general rule of thumb is, however far apart the sensors are, is how deep they can sense. So if they're 10 meters apart, they can sense they can determine internal structure for 10 meters below. That won't help you much on Europa. You're going to have to get like half a planet away from each other, basically. So you got to place, excuse me, sorry, Dr. Pepper. So if you set up a network, you're going to have to set these things up far away from each other. They also have to have the same internal clock. They have to start at the same time, because when the waves hit, they have to measure the time difference between one measurement of a wave and another measurement of a wave. Very important. The time is extremely important, and that's often overlooked. And you have to have good contact with the surface. What good means, I don't know, but yeah, when the surface moves, your probe has to move. You want the surface, you want the probe to move with the surface. So you want it to be basically fixed to the surface as good as you can do. The issues with internal structure, seismometers, like I said before, seismometers are not known for being robust. They're like mass spectrometers. They're very dainty devices. Seismometers might be a little bit more robust than a mass spec, but you're not going to be able to drop it from orbit, okay? If you hit the ground way too hard. Now, accelerometers can tolerate high impact, high G loads, but they're not as accurate as seismometers. However, something is better than nothing, okay? So if your seismometers are going to hit the ground and destroy themselves, your accelerometers will hit the ground and not destroy themselves, but they might not measure as accurately. You got to go with the accelerometer on that one, right? And they're also much smaller. So accelerometers are. So surface orientation is a big deal too. If your probe lands like this, or lands like this, or lands like this, is it going to affect the measurement? Is it going to impact how it measures? I hope not, because unless you can control how it hits the ground, then you need to put something that can measure in all 3 axes on there. And then if you are near a lander, landers are really, really bad for seismic measurements, because landers are loud seismographically. Landers create their own vibrations, essentially. They get hot, they get cold. The ones on the moon, like I said before, there's seismometers on the moon. And I've talked to these lunar scientists, and they're so mad because they didn't know this in the 60s when they put the seismometers there, but the seismometers are right next to the lunar landers. They're like, lunar lander, the astronauts walked out, seismometer. They didn't think about it, but the lander itself gets hot and gets cold, and it crackles and pops and makes all sorts of noises, and there's whooshing sounds and stuff like that. And so for the seismometer, all it sits there and all it's doing is listening to the lander. You know, it's not able to hear the vibrations from the ground itself because the lander's too loud, right? It's like a bad neighbor essentially. So get away from the lander, at least 100 meters minimum. How long do you operate? Maximum is going to be 30 days, 30 Earth days, because that's how long the mission lasts. And then how are you going to power your stuff? How are you going to communicate back? How are you going to thermally keep it insulated? Radiation's a big deal on Jupiter. How are you going to make sure it doesn't fry itself? You know. So at the same time on Europa, your probe could simultaneously fry and freeze because of the radiation and the temperature. How's that for cool? So creating a seismic network, if you want to look at a seismic network, here's some, I'm just going to go a little more detail with this. There's two options for creating a seismic network. There is dropping a probe and just having it hit the ground and bounce around and then come to a rest, or you can have a probe that hits the ground and buries itself in the ground, okay? Now, the probe that goes and penetrates the surface and buries itself in the ground, it's going to have a better reading seismically. When the ground shakes, it's definitely going to shake because it's in the ground. It's touching on all sides of it. It's part of the ground, right? However, it's a huge impact. That's a lot of G's it's going to feel. And also, it's surrounded by soil or surrounded by ice or whatever. And the impact angle is a big deal. So it's called a penetrator when it does that, when it hits the ground and then buries itself in the ground. We do this a lot with missiles actually, because now we're fighting people who are not on the surface of the ground, on the surface of Earth. We're fighting them in caves that are meters and meters below the surface of the Earth. So we have missiles that hit the ground and go 10 meters deep and then explode, rather than hit the ground and explode on impact. So we've gotten really good in the last 15 years with penetrating missiles and stuff hit the ground. So penetrators, science-wise, are the same kind of principle. Now, remaining on the surface, having a probe hits the ground and then just kind of comes to rest, the probe feels fewer G's because it slows down over a longer period of, over a longer distance. However, there's opportunities, there's radiation on the surface of Europa. There's that will impact it because it's exposed now. And also, there's the potential that the ground might move and the probe might not move as well because it might not be fixed to the ground very well. There's issues with that. And it could damage itself, too. So you go over this stuff if you want to create a seismic network. So these are two graphics, my beautiful graphics I created. So the orbiter is going overhead, penetrating the surface, basically have a missile-shaped thing that hits the surface and digs deep, or something that just comes to rest on the surface. That's the two basic traits, and there's good and bad points about both of them. You guys have to decide what's the best way for you if you want to do this for your science objective. So, temperature and heat flow. Temperature measurements, they're basically both the same measurements, but it's just how you measure the temperature that separates temperature and heat flow. Temperature measurements, the objective is to understand the thermal environment of the entire surface of the planet. If you're saying I want to create a temperature network over the planet, you want to measure temperatures all around the planet. That's the objective of a temperature measurement. Now, heat flow is a very precise measurement in one location where you measure temperature and then you go down below the surface to measure, okay? You're not measuring on the surface around, but you're measuring surface and down low, because you want to measure, does the temperature change as you get deeper into the surface? Like on Earth, caves. When you get to a certain distance below the surface of the Earth, the temperature is just constant. It does this on the moon as well. We have heat flow measurements. The astronauts did this on the moon. There's some really cool pictures. It looks like the astronauts are on pogo sticks, but they're actually trying to push these things on the ground because the gravity is so low on the moon. The astronauts are pushing these things. They're like a meter long. And what they found on our moon, on Earth's moon, is that yes, after about a quarter of a meter, maybe 0.3 meters, the temperature of the moon is constant. And so what does that mean for us? That means if we ever make a moon base, then we make a base and throw a bunch of moon dirt on top of it, and we'll be good, right? Because it's like in a cave. It'll be insulated from the harsh environment outside on the surface. And so heat flow measurements are very important. It also tells you something about the inside of a planet. If there's a huge heat flow, that means there's a big heat source down there, On Europa, they think the heat is generated by the tidal flexing. So you should be able to correlate tidal flexing with increased heat flow. Does that happen on Europa? We don't know. We've never done this before. So that's temperature and heat flow. The measurement that you use, the device that you use called a thermocouple, I'll explain in a second, it's the same measurement. It's just basically it's a wide network versus very precise, one location, very small location, but you're taking measurements down below the surface. That's the difference in temperature and heat flow. So the temperature network probes are all over the surface. It's a network of probes. The farther apart the better, the more the better, just like with seismic readings. This implies they'll probably have to fall from altitude because the lander is going to be at a certain location. So you have to sprinkle these things all over the planet from altitude. Heat flow. This is my graphic. This is below. The red is hot and then blue is cool. So it's getting cooler as it goes up. This is assuming there's some energy source down below. So scientists believe there's very little temperature difference between the core and the surface of the planet. Sometimes there's a big difference, but they want to know the temperature profile. They basically want to know what's the temperature profile at a depth. Now, how deep you can go depends on your resources, how much mass you have, how much of an impact you can tolerate, what the surface is made of. So you might only be able to measure like a meter deep or something. But that's a meter that we didn't know about beforehand, okay? So that could tell us a lot of information about the heat flow, measuring a meter. Is there a difference in, meters like what, this long? Is there a difference in temperature from here to here in the surface? If there is, that's a really interesting finding, okay? So that's heat flow. Again, temperature would be measurements all along the surface. Heat flow is one location, but down through the surface. Same measurement. You're measuring temperature essentially, but there are different ways to implement them. Temperature measurements of the surface, blah, blah, blah. Distance between the temperature measurement is known. So it's important with the heat flow measurement that you know the distance between the measurements. That's very important. How much did the temperature change over a certain distance? That's very important to know. Heat flow. So if you want to measure, if you want to get below the surface, how do you do this? There's three basic ways. I won't go into them now. If you have questions, we'll go into it later. The Germans, the Deutsch Luft- and Raumschaft, DLR mole, is it's a little device that made to dig below the surface, but it takes a long time. There's a drill, the standard way to do it. Drills are nice, but they're heavy and they require a lot of power. And then there's a penetrator, which is what I talked about earlier, which is something that uses kinetic energy, hits the ground, and then it buries itself in the ground. Those are three basic ways to get to a depth below the surface. Now, temperature-wise, how do you measure temperature? What actually measures temperature? I mean, is it a thermometer? Is it mercury? What? Typically, temperature measurements are done with thermocouples. Now, a thermocouple is just like the name would suggest. Thermo is temperature. It measures temperature. Couple means two, right? So a thermocouple, the book definition is two dissimilar metals that are sandwiched together, and then they're just basically used to measure temperature. What happens is you have these two metals and they're together. But it's just a wire. This is a thermocouple. It is just a wire, okay? But these two metals are placed together. And then if you heat it up, then one of the metals, what happens when you heat up metals? They expand and contract or whatever, right? So the different metals expand and contract differently at different rates. So if you heat it up, it might do this. If you cool it down, it might do this, right? And so what happens is at the interface between these two metals, at the interface, there is a voltage is induced by the contraction and the expansion of the two metals. That induces a voltage. That voltage goes into a computer and is measured by a computer. And then the computer is calibrated so it knows, okay, this much voltage means 5 degrees or whatever, right? That's how it works. That's how a thermocouple works. It's basically it's a wire. It is essentially a wire. They're very light. They do not require power. From an engineering standpoint, they're beautiful because it's a wire that requires no power and you just monitor it. You just monitor the voltage that comes out of it. It's beautiful. Now a pressure transducer, I talked about earlier, measuring pressure, they work very similarly. A pressure transducer, just imagine a diaphragm, right, or some sort of disc, right, and there's a diaphragm stretched across this disc. Now the pressure pushes down on it, right? You've got this, just imagine a tube like a straw, and there's this diaphragm inside the straw, and then there's a the diaphragm is a membrane that's over the top, right? And so if the pressure on the outside of the straw is higher, then it pushes down and it flexes inward, right? The pressure on the outside of the straw is lower, then it bows up because the pressure inside is higher. This motion of this diaphragm, this pushing or bowing, induces a voltage, which is sent to a computer the exact same way. So it induces a voltage that's measured by a computer. That voltage is calibrated so they know, okay, that voltage means it's 5 psi difference or something. So that's how pressure transducers work. It's the same, basically the same principle as a thermocouple. It's an induced voltage measured by a computer. So a pressure transducer does require a little bit of power just to keep it working. But thermocouples are beautiful, they don't require any power. Issues with temperature and heat flow, you gotta have good contact. To measure temperature, you have to touch something. There's those little laser temperature measurement things. Those don't work for anything. Those are kind of crap, okay? In a pinch, scientists might use them, but they don't work very well at all, basically. Location and time has to be known. For heat flow measurements, you have to know the distance between the measurements to measure accurately. The lander, if you're close to a lander, it's going to influence your temperature measurements, or if you're close to something that might, if you're in a shadow or something, it might influence temperature measurements. Those are going to be influenced by that. So anything that would influence the temperature is going to influence your temperature measurement. Thermal short, a thermal short, just like an electrical short, is when you put like a metal between two things. That's an electrical short. A thermal short is when you connect two things, like if you have a hot here and a cold here, and you put metal between them, they're eventually going to get to be the same temperature. That's a thermal short. You've shorted it thermally. So if you have your device here, your probe here, and you've got temperature measurements, you can take along your probe. This thing broke. You want to make sure that your probe doesn't conduct heat down it, because you're taking a temperature measurement here, 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 here. If your probe was conductive, was a metal, then they're all going to measure the same temperature. So you need to make sure that you don't have thermal shorts in your temperature probes. Magnetic fields, they are, magnetic fields basically are, it's an interaction of electrical fields and magnetic materials. Usually the letter B is used to, is the abbreviation for magnetic fields. It's got a vector symbol on top of the B because magnetic field has a magnitude and direction, it's a vector. It's produced by moving electric charges and the intrinsic magnetic properties of some elements. So you have electric charges that move, you create magnetic fields. So there's some metals that have intrinsic magnetic properties. So how do you measure magnetic fields? You use a magnetometer. A magnetometer, not a magnometer, a magnetometer. Magnetometer. So very simply, it is a coil of wire. It is two coils of wire, actually. It is one big coil of wire that is a voltage is applied to it. And so there's current running through the wire. Basically what you've done is you created a very, very small magnet with this wire. It's called a solenoid. There's another solenoid, another coil of wire sitting right next to it. And that coil of wire is not, there's no current running through it, but it's monitored, okay? And so what this does is this magnetic field influences this coil of wire, but it's known, it's a known value. And so what happens is if you take this magnetometer, these two magnetic fields, and you put them in another magnetic field, this magnetic field is changed. The magnetic field that is set up by the magnetometer is changed. That change is felt by this coil over here that's just sensing. This sensing coil feels the change, and it can tell, because they've calibrated, it can tell how much of a magnetic field it just felt. That's how magnetometers work, essentially. There's a flux gate magnetometer is the most popular kind for spacecraft. This is the flux gate, very, very small. Magnetometers are great. They're small, about the size of a deck of cards. This is kind of big for a magnetometer, but the size of a deck of cards. The only thing bad about magnetometers is they are antisocial. They measure magnetic fields indiscriminately. They will measure the magnetic field of a planet, of a sun or a star, but they'll also measure the magnetic field of a processor. So if you put your magnetometer next to a computer, it's going to measure the magnetic field of that computer. on the image of the IMU earlier, it had a magnetometer on board. That's okay because they've calibrated that magnetometer with that entire board. They calibrated that magnetic field out of it. So it knows what it knows, it already knows it's there. So you can calibrate magnetometers if you have to put them near electrical devices, but generally speaking, magnetometers like to be isolated. That's why on spacecraft, they usually put them at the end of 10-meter long booms. That's, I mean, they have to get it so far away from the spacecraft that it doesn't measure the magnetic field of the spacecraft, it measures the magnetic field of the planet that it wants to measure. So these little devices are simple, they're awesome, but they're antisocial. They don't like being around other things. So those are some measurements. These next 3 charts are gonna be the tables that you have to use. Again, when we come back to see you guys next week, we want to see as much of these filled out as possible. This first table is the science traceability table. And the first thing you list in this table, the far left column, is what is your science objective? What do you guys want to measure? As an example, I put internal structure here. And it's because it's an interesting measurement, and mainly because the second column here, measurement objective. The first measurement is science objective. What is the big science question that you're asking? We want to know what is the internal structure of Jupiter, of Europa. That's your big science question. What's the internal structure of Europa? And so internal structure is your science question. What are you actually, measurement objective, what are you actually measuring? Again, you're not going to take your internal structometer, put it on the ground. No such thing exists. What you're actually measuring are the quakes, the vibrations, the waves that go through the planet itself. That's what you're actually measuring. In order to determine internal structure, you're actually measuring vibrations and waves, okay? So that's what this column is. What are you actually measuring in order to satisfy this science objective? You know, your science objective could be, what is the heat flow of, on Europa? What are you actually measuring? You're actually measuring temperature, okay? What? What are you laughing at?
You said actually like 10 times.
I know. Sorry, I hate it when people do that. So, but this is a lot of actualities. So, so science objective. What is your science question? Measurement objective. What is the measurement you're going to make that answers this, that will satisfy this science objective? Measurement requirement. The third column. How are you going to measure it? What are the stipulations you're going to have? So if you do magnetic field, if you do internal structure, you have to have at least 3 probes because you have to have a network. You're going to stay on the surface, or you could penetrate, or you could go beneath the surface a little bit. This is some of the stuff in this column. You guys decide these things, okay? Some of the things you don't decide, some of the things you do decide, okay? And I've said arbitrary 4-hour lifetime is what I want to say for ours. Yours could be a 30-day lifetime if you want it to be. And we're going to measure continuously. You guys decide these things. You might not be able to, this is going to be the hardest column that you have to fill in. We will work with you on this column because some of these things you decide, and you don't know enough right now to decide these things. We will help you with this, okay? But you do know, like, internal structure requires at least 3 probes. The more the better, right? And you have to measure the surface vibrations, the lifetime, and then the how it's measured I made up, okay? That is something I decided, and for this example I just made it up. And then what is the instrument we're going to use? We're going to use an accelerometer, okay? So the science trace matrix starts out with your science objective, then walks you through to the instrument you're going to use, okay? So we've got our big, grandiose, what is the internal structure of Europa? And we're going to use accelerometers to determine that. And along the way we're actually going to measure waves and vibrations, and then we're going to measure them in this way. That's what the third column is, and the last column is the instrument we're going to use to measure it. Now the last column feeds into the very next table. It's really just one big table, but we split it up. So the last column on this page is the first column on the next page. I switched examples, probably shouldn't have done that, but I switched examples. So your instrument, you could use a mass spec. Now this is where you say, okay, your instruments are going to start to give you requirements that you want to know. It's like, what are the qualities, what are the attributes of this instrument? The mass spec that we found, it weighs 0.23 kilograms. It requires 1.5 watts of power. It creates 2.4 megabits per second of data. Our lifetime frequency and duration, you guys decide these three things. It's described in the book. Lifetime is the total lifetime. How long is this thing going to exist? I'm going to be taking measurements. From the first measurement to the last measurement, how long is that? Total lifetime. That's lifetime. Frequency is if you turn this thing off and on, how long do you turn it off and on? The best example I have is for your smartphone. Okay, your phone, you turn it, it's on right now, right? And but what do you do with your phone? You don't leave your phone all the time. I mean, if I left my phone like this on all the time, what would happen to it? Battery would run out, right? So let's just say for 1 day is the lifetime of this phone. What do I do when I'm not, I just got an email. What do I do when I'm not talking on my phone? I shut the screen off to save battery life, okay? So let's just say that I look at my phone for, every 10 minutes. I look at my phone for 1 minute every 10 minutes, okay? So for 1 minute, I open up my phone, I look at it, I read my email. Oh, I got an email from my sister-in-law, interesting. So I really did, just got it. So and then I turn it off. I look at it for 1 minute, turn it off. 10 minutes later, turn it back on for 1 minute. Look at my email, turn it back off, right? That is frequency and duration. The frequency is how long is it between, so if I look at my phone for 1 minute every 10 minutes, the frequency is 10 minutes. What is the time that it's off? It's off for 10 minutes. How long is it on in between offs? It's on for 1 minute every 10 minutes. So the lifetime for my phone is 1 day until I charge it at night. I put it next to my bed and I charge it. Literally, I do this. And so 1 day. And then the frequency and duration are every 10 minutes, I look at it for 1 minute. So that's what lifetime frequency and duration mean. The best example is your phone. Because everyone is familiar with these things, and you know that if you leave it on all day long, you're going to run out of batteries. You're going to run your battery down. You don't want that. It's the worst thing in the whole world. You're like, I've got 10%. I need to find power. I've got 10% battery left. What am I going to do? You're just like, stressed. Isn't it stressful? It's kind of funny. Like, I'm down to 20% battery. I need to find the battery backup stat or a car charger or something. I'm going to, So same thing is true with your probe. Total lifetime. And what this does, the exact same thing. We use these three columns to determine how much battery you need for your probe. That's why this is important. Okay. So the total lifetime of your probe is going to be alive. Maximum for this mission is 30 days because that's how long we're at Europa. And then, so we're saying every 12 hours we're going to measure for 5 minutes. Now for a mass spec, that might not be the smartest of measurements. This is a terrible example because mass spec measures constituents. Now, are the elements going to change every 12 hours? I don't know, maybe. They might. We can tell. That's kind of overkill. We might not need to do it for 30 days, right? So we can determine whether this makes sense. This does not make sense for this. Okay, I'll just go ahead and tell you that. We'll talk about this with you guys in class, though. That's what our job is. The next time we see you guys at your team progress report, you will present this to us. We'll talk to you about it if it makes sense or not. Other examples of thermocouple. It weighs 0.2 kilograms, usually per meter, because it's a wire. It's in terms of distance. Doesn't take any power really. It creates 0.1 megabits per second of data. And so because it doesn't require power, most thermocouples are just used constantly. They're just always being monitored, okay? Now the computer that it's plugged into requires power. That requires power, but the thermocouple itself does not require power. So we use it for 30 days, going to be on continuously the whole time. Because we don't care, it's a thermocouple, right? Now, how do you fill this in? You guys look online. Look in the book. There's some references. There's CubeSat websites that take you to. There's CubeSat instruments are a great resource for science instruments. There's also page 40 in the notebook gives examples of different types of instruments as well. It gives these are from the notebook itself. So there's no excuse if you can't find an exact match for an instrument that you want. Look on the page in the notebook, and you can use that data for a placeholder, at least for the time being. But it's pretty representative. You can use that. But there's CubeSatShop.com, which is mentioned in the book. There's Wattlow is mentioned in the book. There's Omega mentioned in the book. There's places to find these instruments. This is the hard part. Finding instruments is hard. We try to give you more resources with that. So I just mentioned that a thermocouple requires a computer for it to work because it's just a wire. It's got to send the voltage somewhere. So you're also going to have support equipment that goes along with your science equipment. Your science equipment just measures science. It can't operate by itself. It has to have a computer. It has to have a brain to work. And so there's support equipment that we'll talk more about in the future here. We're going to talk about functions later. But go ahead and get this started because you know you're going to need certain things. And page 41 in the notebook has a list of support equipment that you can use. A computer is a big one. The computer that we have is from a CubeSat. It weighs 0.094 kilograms. It weighs 94 grams, okay? 1 gram is 1 paper clip. 94 paper clips. Very, very small, very light. It's just a chip. It's just a little chip, right? We don't need like a, the computer in your phone is overpowered compared to what you need for this. It requires 0.4 watts. These are the technical specifications on the computer. So you can do this with other things. What are the other support equipment they need?
Antenna.
Huh?
Antenna.
Antenna, that's right. You need a transmitter, which is basically a specialized computer. You need an antenna. You need the transmitter to transmit the data. The antenna is how you transmit the data. It's like, an antenna. You need other support equipment. Look on page 41 in the book to find the support equipment, to know what you need. And we'll talk more about this in lessons to come also. So this is the last slide. I think I took too long. I'm sorry. My bad. You can fast forward through some of this if you haven't done it yet. So if you have any questions, again, these last 3 tables, we're going to look for these 3 tables when we come to see you guys next week. Okay, so please have as much of these completed as possible. This is the most important table you create the entire semester. This table is everything. It starts off with your science objective and ends with instruments. This is everything. This is your entire mission summarized in a single table. This is an important table, so spend some time on it. If you need help, we're there. The instruments, you can look at this presentation. You can look in the book to find examples of how to measure things if you want a certain science objective. If you come up with a certain science objective and you don't know how to measure it, let us know. But basically everything boils down to properties and composition. Don't forget that, properties and composition. How do we measure the properties of whatever we're measuring? How do we measure the composition of whatever we're measuring? That's what it boils down to, okay? And so then from there you'll go through the instrument requirements and then the support equipment. So we're going to be looking for these 3 tables next week when we come to see you guys. Please have as much information as you can and we'll help you out with the rest. That is it for now. Thanks for your time, and I appreciate your patience with this incredible, amazingly stimulating video. Thanks. See you later.